Pratyush Bagaria. Pratyush is going to talk on the synergistic EDPM UHM WPE stainless steel integrated multi-layer architecture for advanced aerospace refueling applications.
Good evening everyone, my name is Pratyush. I am a third year mechanical engineering student in MIT WPU, and this research is a part of my internship carried out at DIAT Pune under the guidance of Professor Balasubramaniam. He is the HOD of Materials and Metallurgy Department. So first of all, let me just introduce you to what is air-to-air refueling. There are mainly two types of methods for air-to-air refueling. One is the boom type method and the other is a probe and drogue. In the probe and drogue, what happens is, so first let's touch upon boom type. So here if you see, this is a retractable boom that is operated by an operator sitting inside the tanker aircraft. This boom is then extended and inserted into a certain nozzle that is right here on the aircraft to accept the fuel. And then the second system is probe and drogue system. So in this, the tanker aircraft doesn't have to do anything. Its only purpose is to stay stationary and deploy this long probe, long drogue that you can see here, this entire line. So this is a hose. This is a drogue, which is a basket type conical structure inside which this probe tip right here that extends from the aircraft is inserted, and through this hose and through this probe is how the fuel is filled. Now, what is the need for air-to-air refueling? So, air-to-air refueling is extremely necessary because, for example, in long-range missions that are carried out by air forces, what you need is mid-flight refueling. You cannot always land to refuel. That is not just possible every time. So you need fuel mid-flight in the air, which extends your range without having to land or make any kind of stops. So in this, what happens is that there is a tanker aircraft, there is a receiving aircraft. Tanker aircraft deploys the boom or the drogue, and the boom is inserted into the receiving aircraft's connection, or either it is the drogue where the receiving aircraft comes and inserts its probe. Okay, so then some common examples are NATO. For example, the NATO aircrafts, the European Union aircrafts, these guys use a lot of boom type things. And then, for example, the US Navy, the Indian Air Force, these guys use a lot of probe and drogue. Alright. So our problem statement. So our main problem statement is that this hose right here that connects the drogue and the refueling aircraft, this hose up till now for Indian Air Force was imported from third parties, but now since there are certain geopolitical challenges that the world is facing, what we see that the supply of this has been limited and the Air Force is running out of options. So our main thing is that to use a multi-layer laminate to achieve ideal properties required for the proper functioning and structural integrity of this hose. So the laminate that I am proposing today is the material for this very specific hose. Alright? And then our objective. So our objective is to form a composite or laminate structure which withstands the varying multitude of forces and the environmental conditions at which air-to-air refueling is conducted, and also to ensure mass producibility, because it is not just that you make it for once and then it lasts for 10 years. You have to replace it almost every 6 months. So we also have to ensure mass producibility by DFMA. DFMA is designed for manufacturing and assembly. So our design should be simple, cost effective, structurally sound, and also very easy to manufacture. Now, so I will just try to put it into context the environmental conditions at which these hoses operate. Let's say you have an aircraft that takes off in Rajasthan. At Rajasthan, ground level you have 50, 55 degrees Celsius. So from 50-55 degrees Celsius positive, now you take off, you go at 40,000 feet, 45,000 feet. The refueler aircraft is handling temperatures up to minus 50 degrees Celsius. So the temperature range that this material has to handle is minus 50 to plus 50. So that is the major challenge here, to ensure that there is no degradation of the material due to these environmental changes. Also from normal temperature and pressure at ground level to extremely low atmospheric pressure. Compared to ground, it is 0.3, 0.4. So we have to make the material such that it can handle these characteristics. Now, what materials we have used in the structure and why? So for our laminate, we have used EPDM, UHMWP and stainless steel 305 mesh. So why have we done this? First of all, EPDM is a material that is resistant to hydrocarbons and fuel oil degradation. Unlike, let's say, certain metals or certain other copolymers that may dissolve in fuel oils, this one doesn't. Then UHMWP is extremely light, extremely flexible, as we are using it in a woven fabric form, and very high tensile strength. So we are using this to wrap the EPDM in UHMWP, so that it provides a certain amount of strength against burst pressure. And then we are using stainless steel 305 mesh. So just try to visualize it. One aircraft, the second aircraft. From this aircraft, you have a fuel probe coming up to here. These are at near Mach speeds. When they are traveling, imagine the amount of air drag that is there. So the pinching and bending loads can be very easily occurred here. So that is why we use SS305 mesh to give us a certain amount of rigidity, so that the pipe doesn't bend readily. Alright. So this is the structure right here. You see EPDM, then we have a layer of UHMWP, again EPDM, this is the stainless steel mesh, again EPDM, UHMWP, and then again EPDM. So why so many layers of EPDM? Because as I said, UHMWP or stainless steel might not handle the corrosion due to fuel oils that well, but EPDM is very good at it. So here we have laminated EPDM and tried to isolate each and every layer, which helps us in protecting these layers from the fuel oils. So that is why we have such multiple layers, isolating each and every layer of alternate material. And the manufacturing of this was done by heated compression molding. So basically we have the mold which is heated to a certain temperature, in this case 190 degrees Celsius, and then from the top we have another die coming down, and the pressure that this die applies is 10 megapascals. So what we are doing here is we are eliminating the need for an adhesive to form the laminate, because if you add an adhesive, the adhesive might become brittle, it might delaminate at such temperature ranges, variation that is happening. So we are trying to eliminate the adhesive, and just by hot press method we are trying to create a homogeneous layer of EPDM which penetrates the other layers and joins the whole laminate together. So here we have, for 190 degrees Celsius and a pressure of 10 megapascals, we have applied it for a time of 60 minutes to form the laminate. Now the thermal characteristics and properties. So as I told you, it has to sustain minus 50 to plus 50. That means a very high chance of thermal degradation. So what our main purpose behind the thermal characterization of its properties was that to see any sort of thermal degradation isn't being caused in this variation. So we have conducted both normal EDC and extreme cold level EDC. DSC, extreme cold level DSC and also normal DSC, to check a temperature range of minus 50 up to 400 degrees Celsius. So here if you see, this is the heat flow and this is the temperature. So you can see here the heat flow versus the temperature range graph. So here you can see starting from here minus 50 degrees Celsius up to 400 degrees Celsius, we do not see any significant thermal event. So that means it is stable from minus 50 to 400 degrees Celsius. After 400 degrees Celsius, you see this drop, which is the first decomposition, which is of EPDM. Then you see again a rise and a mild drop here. So that is the second decomposition, likely of UHMWP. Because up to 500 degrees Celsius, steel को कुछ नहीं होगा. Nothing will happen to steel. So up to 500 degrees Celsius, the steel is resistant up to 1300 degrees Celsius. So it won't degrade even at 500 degrees Celsius. So this first drop you see is for EPDM, second drop for UHMWP. And as you see up to 400 degrees Celsius, there is no significant thermal event. That proves that our laminate is thermally stable and won't see any thermo-oxidative issues, thermo-oxidative degradation up to that 400 degrees Celsius. Then the swell test. Okay. So now we have the swell test. So the thing with swell test is that we take the laminate, we put it into fuel oil, and then we wait to see if any absorption is happening. So here we see a 51% volumetric expansion upon absorption, and after 7 hours the whole laminate actually saturates and doesn't take up any further fuel, because because this is a mildly porous material, so any fuel oil that has seeped in has filled up all the interstitial spaces. So after 7 hours there is barrier action and any further influx is hindered. Now wear testing. So for wear testing, this laminate when used in a pipe goes faces significant wear, because every time you connect, disconnect, you engage, you draw it back, you deploy it. So a significant amount of wear is seen here. So what we did is a tribological pin on disc wear analysis. For this, in this analysis, basically we are promoting accelerated material loss to see for the time being what the loss, what the reaction is. So here you see 800 to 900 micrometer is the wear depth inside the EPDM right here, up to which the maximum wear is happening. After you see it achieves a steady state, which means after this part, the steady state is the UHMWP, which is as I said, extremely strong, very high tensile strength, doesn't wear very easily. So this steady state graph is what the pin on disc analysis gets the result for UHMWP. And yeah, basically, and it never goes beyond UHMWP, preventing any penetration. Alright, so mechanical characterization. For mechanical characterization of properties, we have simply taken 3 ASTM standard tests. ASTM D3479.
Please try to wind up your talk.
Okay, just 2.
No, only one more minute.
Okay. D5766 and D1599. So in this, what we see is, so this is one of the possible failures here. As you can see, right at the coupling, the laminate, the hose has been broken. So this is due to fatigue wear that we also have simulated for. So to just put it in short, boundary conditions. So basically, there is thermal condition, there is your initial temperature, environmental temperature, which has all been defined, and then the material strength, which for EPDM at various temperatures has been taken up from literature survey. So first, open hole tensile. It can, in open hole tensile, we don't see any significant deformation up to 6,000 newtons. Tensile fatigue. So in tensile fatigue, what we see is that we have up to 8 lakh cycles for which the fatigue will last, and it doesn't show it doesn't show any significant wear up to 8 lakh cycles at minus 80 and 10 lakh plus cycles for 23 and for 50 degrees Celsius, sorry 80 degrees Celsius. Then we have internal pipe burst pressure. So basically when you are transferring the fuel, there is a certain vapor pressure, a certain pressure due to flow rate which is created. So for that we,
Please come to your conclusion.
yeah,
No extra time.
yeah. So for that we have done a burst pressure. Yeah. So as you can see here, for the burst pressure, this is pure EPDM. Pure EPDM goes, it's not clear here, but I'll just tell you. Pure EPDM goes up to 30 mm of deformation, but our laminate only goes up to 0.9 or 1 mm of deviation, which basically supports our theory of using UHMWP and stainless steel mesh, which gives the strength to the laminate. Right? Also, von Mises stress is here up to.
Please.
Okay, sure.
Last.
These are my references.
Okay, thank you. Only one question allowed. Anybody wants to ask questions? If no questions, I just want to know what is EPDM and what is UHMWP.
So, sir, UHMWP is ultra high molecular weight polyethylene. We are using a bidirectional woven fabric here.
Yeah,
Of
EPDM.
EPDM is a kind of rubber monomer, ethyl polydiene monomer.
So both these polymers are stable at 400 degrees Celsius.
Sir, EPDM is up to 400 degrees Celsius. UHMWP goes up to a little bit more than that.
The next topic is